Hello everyone, welcome back to the lecture series of Learning Theory of Automata and Formal Languages. My name is Binayak Parashar. I'm working as an assistant professor in the Department of Computer Science and Engineering at Ajay Kumar Garg Engineering College. So we are here, we have tried to cover up almost maximum of the topics in unit number 1, and we have started off with unit number 2 in the previous lecture. So almost 11 lectures has been covered up in unit number 1, where if anyone have not gone through those lectures, I would suggest go through those, because without the involvement of those videos, it will be tough for you to get the related videos with these particular topics. Okay, so in the first unit, we have covered up about theory of automata, basics of formal finite automata, where we have tried to learn about deterministic finite automata, non-deterministic finite automata, Mealy-Murray machines, equivalence of them, minimization also. Okay, and also we have seen some of the basic properties of finite automata. Now, in this unit, in unit number 2, that is the second unit, or in the syllabus, maybe it's mentioned as section B. So it comprises of regular expression and regular languages. So in the previous video, it's an extension of the previous video only. In the previous video, if you have not gone through the previous video, please go through it. There we have mentioned or explained what is the concept about regular expression. We have seen what are the operators being involved, and also we have seen almost 10 examples, 10 exercise questions, where a language can be represented into a regular expression, and that particular process we have seen. Okay, now we will try to look a little bit of extension of that particular topic, and let's check it out, what is all present in this particular video. So welcome, this is lecture number 13, and the topic name is regular expressions and its definition. Okay, I have mentioned the same topic as its previous class, but here we will be having some sort of extensions to this particular topic. Let's check it out, what are the topics. So first of all, we will try to look into some of the transition graph related to some of the basic expressions. This is very important, because once we cover up these particular topics like regular language to regular expression, then regular expression to finite automata. Also, we have to see finite automata to regular expression. Okay, so basically, if suppose you are having a regular language with you and some of the other, you are not able to analyze that what will be the finite automata for that. Some of the other, if we know how to format or how to express that particular language definition, then from that regular expression, I am able to design a finite automata, then my problem will be solved. So this is a way of representation of a language, and from this representation, we can get a finite automata as well. And also vice versa. From the finite automata, we can also find out the regular expression. So overall, in this unit, 80% of the topic we will be covering over here. After that, we will check it out that how to identify that a language is regular or not, which is a very important topic from exam point of view, and from you can say competitive exams point of view, if you are preparing for GATE examinations and all. Okay, so let's check it out first, that how a regular expression can be converted to a finite automata in this expression, in this particular video. Okay, so overall, if you can look into some of the basic primitive expressions we have taken, if we talk about a phi, let's check it out. What is the concept behind phi? Okay, that is the initial part, and we are having an initial state. You can pause the video and think of it. Do we need to make it as a final state? No, we are not going to make it as a final state. Correct? Next comes expression for A. A is a single transition, so I have put it over here. A. I hope it is got. It's like understandable from your side. That is, A is a single string, and we have put it into the expression, into the transition from the initial to the final state. Therefore, this A is accepting, correct? Because it is reaching the final state. Next comes A plus B. If you look into A plus B, I will take the same transition. In the same transition, A will also be going. In the same transition, B will also be going. In the same way, this particular diagram can also be drawn in this way. We are having an initial state, and we are having two transitions going to the final state. Let me make named as A and let me named as B. And these two transitions are what? A and B. So this and this both are same. See, both A and B are going in the same direction from one state to the final state, and definitely as we are trying to accept this expression, definitely it should reach where? Final state. Got it? So both the diagrams are same. Next comes A dot B. I think in the previous video also in some or the other I have mentioned this particular topic. A dot B. That means I am trying to concatenate. String A with whom? With B. This is my meaning of this particular sentence. I'm trying to concatenate. How do we concatenate? We need another state for it, right? So therefore the diagram will be like this. Initial state, one transition will be for A, B. So let me name it as A as the initial state and C as the final state. So A dot B. If I have A dot B dot C or ABC, then A one transition, B another transition, and C will be another transition, and thereafter C transition will reach the final state. Clear? Next comes A clean closure. A clean closure means what? I will take an initial state, and here I will take A as the clean closure means it's a self loop only, as a strict value starts from where? 0, 1, 2, 3 up to infinity, correct? So it is like a self loop. It will keep on rotating over the same state and keep on giving you the values, correct? But if asterisk value equals to 0, then initial will be what? Final, because asterisk value equals to 0 means what? It will be epsilon. So that means this state will be initial also and final also. So this is how we represent the basic expressions into the finite automata. So these representations are very, very useful from the upcoming point of view, upcoming examples point of view. Okay. Now let us go with some of the conversions, okay, from regular expression to finite automata. It's mentioned over here. Question number 1 says, design the equivalent finite automata for the following regular expression. It is mentioning only to design an equivalent finite automata. They are not expressing that whether you need to find out a DFA or an NFA. Okay. So A B star. So A B star means what? I can write down like this, that it is A dot B star. A dot B star. So that means I will first draw a state, initial state. From here I will initialize A transition. This is suppose state A and this is suppose state B. So A is done. Now for B star, do I need to take one more B over here? No. What I have to do? I have to take a self loop over here as B. If asterisk equals to 0, then this will become what? Final. So therefore this will also become as a final, because asterisk value starts from where? 0, 1, 2, 3. If it is 0, then this will be becoming final. So that means this will be nullified. Only the expression will be A. If it is 1, then A, B. If it is 2, asterisk value 2, then A, B, B, A, B, B, correct? If it is 4, asterisk value is 4, then A 4 times B, A 4 times B. So this is how you can draw the finite automata from a regular expression. So it becomes a little bit easy right now. Okay. Next question comes AB plus BA. So that means here what is happening? AB is also going in the same direction, and also BA is also going in the same direction. I hope it is clear. AB plus BA. Later on I will check this particular point. Correct? AB is also going into the same direction and BA is also going into the same direction. So how to make it? How to design this? Let's check it out. Let me take an initial state. Okay. From an initial state, what I will try to do, see, this AB, although it is going into the same, this AB and BA, although it is going into the same direction, but some way or the other, it is acting as a self loop. Why? Because asterisk is there. So can I take one more state, and from A, it is coming back, correct? So definitely this will become the final state, because if asterisk value equals to 0, then this will be nullified, then this will be initial only final state. Similarly, I have to take one more state, and from here BA will be another transition. Now tell me, A, B, B, A are coming to the same, are going out from the same state and moving to the same state, correct? So definitely AB star and BA star. So actually we will be looking into one identity in the upcoming classes, in the upcoming video, where R1 plus R2 whole to the power asterisk is equals to R1 star plus R2 star. This particular expression we will be by basic identity we will be looking, but overall we will not be considering this, because if you look into the identity, yes, it is expressing, right? AB whole to the power star plus BA whole to the power star, correct? Why plus? Because both are coming out from the same state and going to the same state, correct? So this is the final expression for question number 2. Let's go back to question number 3. Question number 3 says that, again the same question, we are just focusing on the regular expression, don't read the same statement. A plus B whole into C. So we know A plus B. What is the meaning of A plus B? A plus B means I have taken an initial state and I have taken another state, and A plus B. So A comma B, or you can draw A one transition and B another transition. That's completely dependent on you. So A plus B is done. Dot C. This means what? A plus B dot C. So dot C means what? I have to take one more transition and this will be your final state. I hope A plus B dot C is clear to you all. Okay. Now move back to question number 4. Question number 4 says that this means what? A dot B dot C whole to the power asterisk. Nothing is there in between means what? Dot is there. Okay. That means first I will draw, take the initial state. This is completed. Then I have to take one more state as B. And here what is happening? It is happening B dot C. B dot C. What I have to do? I have to take one more state, say suppose C, and I have to make B as the final state, and I have to make a transition for B and a loop back to C. So now look into this. B dot C, B dot C, B dot C, B dot C, B dot C. It will keep on rotating. So it will act like B dot C whole to the power clean closure, and remaining part is for A. Correct? So this is how you can design a particular finite automata for a given expression. Let's go to question number 5. Question number 5 is a little bit of a, not a small expression, it is a bigger expression. It says that A plus B whole to the power clean closure into ABB plus A positive closure B. Now we remember that clean closure starts from where? 0, 1, 2 up till infinity. And whereas positive closure starts from where? It starts from 1, 2, 3 up till infinity. That means only 0 is not present in the case of positive closure. And also we know that A to the power clean closure is equals to A dot A to the power positive closure. This thing also we know, right? So some or the other it will help us in doing the expression. Okay. Now what I will try to do, if we are having a bigger expression, we will try to subdivide that expression into 2 parts. 2 parts or multiple parts, how many way you want to it. So what I do, first I have done A plus B whole to the power clean closure I have taken. What will be the diagram for it? See, this is A and this will be the final state, and here I have to take A comma B. See, A and B are going out from the same state and entering into the same state, correct? And that is acting as a self loop. So A plus B whole to the power clean closure. If clean closure equals to 0, then initial will become the final, that is epsilon. Other than that, it will just produce the similar elements. Okay. Now this is done. Now I have to put forward with this expression, right? Step 2, ABB plus A plus B. ABB. So what I can draw, what I can draw is that this means what? This means what? This means A plus B whole to the power clean closure dot, there is a dot operator, right? Followed by ABB plus A. So this is the expression, right? So I have to add one more state with it, so in order to finish it up with this process. So I know ABB plus, so that means some or the other I have to take one initial state. Now just I'm looking over to step number 2 in the second expression, then I will try to submerge it. What I'm doing? One, I'm doing A one I am doing B, and one I am doing B. So this is the final state. I won't be making as a final state name. Okay, I won't be making a name over here. Later on, I will name the states. And the similar way, in the similar state, it is going a to the power plus b. That means a to the power plus means what? Sorry, this one I have made a mistake. Here it will be what? It will be, okay, it will be a to the power plus equals to a dot a to the power clean closure. Okay, so a to the power plus means a dot a clean closure. Okay, now if we look into this particular scenario, overall, if we look into a to the power plus means what? A dot a clean closure, right? So I have to draw a. I have to take one more state, and here I have to draw for a dot a clean closure. Okay. Thereafter, dot b. So dot b will be directly transferred to whom? To the final state. Now look into this particular para. A b b plus a dot a star dot b, and both are going into the same direction. That's why plus came. Okay. Now I need to merge these two conditions with this one. If I have to merge these two conditions, what will be the diagram? The diagram will be, okay, this A will be now made as same state, correct? Initial state. So I will make as A. Here it will be a self loop for AB, A comma B. Thereafter I will transfer this A, correct? Then I make it as B. Then I make it as state C. And then finally I will make this as D. And here what I will do, I will try to take A, and I will try to take suppose E as the state, and here I will be having a self loop for A, and from here I will be having a transition for B. Now I have tried to merge this with this one, and finally I got this diagram. Got it? So this is the overall expression, overall finite automata for this expression. I hope we have tried to cover up almost all the topics related to conversion of an expression to a finite automata. Let's check what is this meaning. What is the meaning of this particular theorem? This theorem says that, Kleen's theorem, this theorem says that how the basic three operators, that is union, concatenation and clean closure, is being used. The same concept, what we have used, the basic operators, that is clean closure, union, okay, union is represented by plus, and then concatenation. How these three operators are being used together into the form, and if it is used, then definitely that is followed what? Kleen's theorem is being followed. Theorem says that for any regular expression that represents language L or for a particular expression R, there is a finite automata that accepts the same language. Definitely, because regular expression is what? It's an expression, or it's a representative for a particular language. So if we are getting a particular expression which is representing the same language, and in that language we are using these three operators as the basic media operator, then definitely that is the main concept behind this theorem. Okay, the theorem says the same thing what these three operators generally describes. Clear? Next comes Thompson's construction. Now this is one of the important concept behind conversion of a regular expression to an epsilon NFA. Okay, Thompson's construction, actually its full name is Mac-Norton-Yamada-Thompson's algorithm. What this particular algorithm says, it says that how we generally convert a regular expression to an epsilon NFA. Till now we have seen what? We have seen only the conversion process of a regular expression to a finite automata, where we are not including any kind of epsilon transitions, correct? But if we need to include any kind of epsilon transitions into the particular finite automata, that automata will become what? Epsilon NFA. Clear? So that means for conversion of such kind of thing, we need to follow this particular algorithm. Okay. Now let's check some of the basic operators and their Thompson's construction. A plus B. How do we convert this particular A plus B into the case of epsilon NFA? Okay. Normally, how do we represent in finite automata? We represent in this fashion, right? A comma B. Now, how do we represent over here? See, A comma B means what? This is nothing but we are having one initial state, and there is one transition for A and another transition for B, which is going to the same final state. This is the meaning of A plus B. But how do we represent with epsilon NFA? Let's check it out. I will take a state. This thing you need to remember. This particular process you need to remember. I have to take one two states over here, and this state will represent for A transition and this will represent for B transition, and this will be your final state. Let me name the states as A, B, C, D, E and F. Okay, and remaining transitions will be your epsilon transitions. This is how A plus B is represented in the form of an epsilon NFA. I hope this is what you need to remember. How do we remember this? A part is being represented with these two states, B part is being represented with these two states, and remaining from the initial and to the final, we will put the epsilon transitions. Clear? So this is how it's being used over here. I have shown it to you. NFA is the diagram. This is what I have drawn for a single NFA. Okay, and for epsilon NFA, I have shown it to you. Correct? Now let's go with the next expression, A dot B. For single NFA, the diagram will be like this. Correct? Okay, and for epsilon NFA, the same concept. Epsilon NFA means what? This means what? A dot B. Then something is separating this A and B. For this separation, I will just put an epsilon transition. How? This is A transition is there, B, and this is another state, say suppose C, from here B, and this will be making as a new state, as a final state, D, and A and B separated, the separated part we will put as epsilon. That's it. That's the only difference between A plus B in the form of an NFA and A dot B in the form of an NFA and A dot B in the form of an epsilon NFA. Now next basic primitive example is for A to the power clean closure. For a single NFA, we generally draw like this. Correct? We draw like this. But in the case of epsilon NFA, how we will draw it? See, if asterisk value is equals to 0, then A initial state will be the final state. Correct? So I will take a final state over here, and I will directly transfer a transition for epsilon over here. If asterisk value equals to 0. Then this thing you need to remember. Okay. Then next for A, single A, what I will do? I will draw an epsilon transition. I will take another state. Again, I will draw an epsilon. This I won't be taking an epsilon over here. I will be taking A transition over here, and then this one epsilon. But in order to make this A as a self loop, I will just backtrack here as a epsilon transition. If you look properly over here, epsilon, in this particular these two states, A is acting as a self loop. See, A, epsilon, A, epsilon, A, epsilon. Epsilon means what? 1. So A dot 1, A dot 1, A dot 1, A dot 1, followed by what? It will give you a self loop of A only. And if asterisk value is 0, then directly from the initial state, there is a transition for epsilon. So this is the way how you represent for A to the power star in the case of epsilon NFA. Okay. So this is all about for a given question. Now we will do the last question. This is an example where combination of all these primitive examples we have done it. See, these are the primitive questions that I have done it. A plus B is one primitive expression. A dot B is another primitive expression. And we have seen A to the power star is another. So these are the primitive expressions which you need to remember. Now we need to combine these two and put it into one expression. How to do that? First, I will try to differentiate this A plus B as separately. Later on, I will add this concatenation one. First, I will try to do this. A plus B, I know. A plus B, I know. How to represent A plus B? We make epsilon transition, and here A, okay, here epsilon transition, and here is the final state. I'm not making this as a final state as because the expression is not yet done. Correct? So let it be as a, this is the overall diagrammatic representation of epsilon NFA for A plus B. Correct? If I have to make A plus B whole to the power clean closure, then definitely I need to introduce one more initial state, and this will be your epsilon transition. And I have to make one more epsilon transition and make this as a final state. If asterisk becomes 0, then initial state to final state, there will be a epsilon transition. Correct? Look at this diagram. A to the power clean closure, right? From initial state, there is an epsilon transition. From initial state, there is an epsilon transition. And this part is for A, and this will be for A. Correct? Now, is this a to the power clean closure or A plus B to the power clean closure? No. What I have to do? I have to do a backtrack of it, and I have to do a epsilon transition. Now this A plus B whole to the power clean closure it will act. Done. So that means this particular part is done. What I have to add? I have to add A. So what I will do? I will do one more. So this is till here it is an A plus B whole to the power clean closure. I have to take one more epsilon, and then from here I have to take A as the transition, and this will be your final accepting state. See, till here it is A plus B whole to the power clean closure. How do we represent A dot B? We represent B in between that, we put an epsilon transition, right? So same way I will be putting here also A plus B, then epsilon, then dot A. So this is how we construct a particular expression in the form of a epsilon NFA. So what is the methodology that is being used? Use Thompson's Yamada algorithm, or Thompson's Norton-Yamada algorithm, or simply Thompson's construction algorithm. So therefore, in this particular video, we have tried to understand how a particular regular expression can be converted to a finite automata. Okay, and also we have seen a particular algorithm which named is Thompson's construction for the conversion of regular expression to an epsilon NFA. So in the next video, I will come across with one more interesting topic, and keep watching. Thank you.